for joining today. Welcome to this interactive session on this LAMMPS software package. So the plan for today is that in the first part, I'll discuss general background on stochastic immersed boundary methods and SELM approaches. And then the plan is for us to go together through a hands-on example. My hope is this session can be helpful to you in getting familiar with setting up the models and overall how the package works. Please do feel free to reach out to me and let me know if you have any questions. All right, let's get started on here. So basically the components are a collection of solvers for doing fluctuating hydrodynamics subject to fluid structure interactions. And as I mentioned before, we've kind of in the most recent iteration put together a Python interface and Jupyter Notebooks. And this really leverages machinery and LAMMPS that's sort of doing something very similar. And this gives you access then to a range of stochastic numerical integrators that we've put together, both in the inertial and the quasi-steady state regimes. I'll talk a little bit more about that. I'll kind of skip this for a moment. We'll come back to that just so you understand kind of the pipeline of data and how things are interacting. Again, it's not really terribly important to understand all of those details. It just kind of helps you get a little oriented about why certain things are organized the way they are. So what we've done is rather than trying to reinvent the wheel, what we're doing here is integrating our codes effectively as new thermostats or dynamic integrators for the molecular dynamics package LAMMPS. And the advantage of doing this means that you don't have to implement your own potentials for all of these common things that people do in the coarse-grained and molecular community. So if you want Leonard-Jones style interactions between two particles, you can just write two commands in the script file, and now you'll have Leonard-Jones interactions. If you want to do, particle mesh Ewalds for like electrostatics, similarly, you don't have to rewrite a whole code to do that. You just put a couple of script lines, and now you have, electrostatics, and so on down the line. You can do, harmonic springs. You can do, many body interactions, and so on. So LAMMPS is really wonderful in that way. It's highly optimized. And also there's a lot of tools to do statistical analysis as well. So when you're doing, these types of simulations that are stochastic, you're often interested in getting certain ensemble statistics. And again, you don't have to write codes, to get correlation functions and things of that nature. You can simply, add a few script lines in your LAMMPS input, and away you go, and you'll be able to analyze these things quite readily. So that's what we're aiming to do, is to kind of leverage this whole ecosystem from molecular dynamics, but now to be able to apply that to stochastic immersed boundary methods and related techniques. And so I'll just also mention, if you're familiar with this business, there's all kinds of thermostating that people do. There's barostats that, adjust box size to give you constant pressure. There are things called Les Edwards boundary conditions that allow you to do like sheared simulations. And we're also starting to incorporate that as well with the stochastic immersed boundary stuff. So you can really leverage it again, just as like another thermostat in some sense, to do these mesoscale coarse grain type simulations. So that's sort of the overall arching idea. Of course, there's a lot of details that go into that. And again, in that spirit of trying to make this interoperable with other software packages, we've really leveraged standard data formats like, XML files for configuring the objects that control ultimately the LAMMPS thermostat. And then most of the data is output now in a VDK format of one form or another. And that allows you to then both visualize continuous fields, which is something that you don't usually associate with a molecular dynamics package. So this VDK data really allows us then to kind of leverage a standard format that can be then imported into any of your favorite flow visualization software packages, like ParaView, for example, or other things that people like to use. You could use, well, I'm not going to go into that, I guess. And then you can also, use any analysis tools. Again, you could use stuff like MD analysis and so on, packages in Python. Okay, so that's sort of, some of the governing philosophy. And then early on when I was doing this, this was kind of before Jupyter Notebooks were very popular. This is kind of like MATLAB days. So I actually did end up building my own graphical user interface for building models and kind of adjusting geometries and things, which we've used in various projects. And so I do also have that available, but it's kind of a little bit, I think, given the way that modern workflows operate now in scientific computing, it's a little bit dated in that way. But if it's something somebody would be interested in or has a use case scenario for, I'd be very happy to work with them further on sort of modernizing and updating this GUI interface, which we refer to as Mango here. And so that's all Java-based. It still runs really nice. The great thing about Java is it'll run on any platform, you know, on your MacBook, your Windows or Linux machine. And so I'll show a little bit of that, but you can use this to kind of interact with the model. My original goal was to use that to generate all of these XML parameter scripts and so on in kind of an automated fashion. But again, the modern incarnation now of the Selm interface is now all through this Jupyter and Python interface to LAMMPS. Okay, so I guess I should say that the Selm stuff is all compiled in C, C++. So sort of all of the traditional script files and stuff, you don't have to write those any longer by hand. You basically use the Python or Jupyter Notebook interface, set up your model, basically push a button, and it'll run for those next 1,000, 10,000 time steps. And of course, what's great about Python is then you can do kind of these intermediate spot checks, make sure the code is on track, that things are behaving numerically stable, and so on down the line. Okay, so I've also designed all of the software packages here to be quite modular, so that if there are new stochastic integrators that people are interested in implementing, or new types of immersed boundary methods they're interested in implementing, that all can very easily be done in this framework. It's essentially just creating one new template C++ file. You just put your integrator basically in a certain subroutine in there. Everything will then be ported through LAMMPS. And then on the flip side, if somebody wanted to update anything in the Mango-Selm interface, same thing. It's just a Java class. You put in what the fields are for that particular integrator, and then away it goes. So it's pretty standard now that we have this infrastructure to extend it with the new data types, new integrators, new coupling operators, and so on down the line. And so the idea is that just now I'm pointing to the lower right corner here. This is sort of where our codes are, the Selm time step integrator stuff. And just like in the immersed boundary method, you have different types of degrees of freedom, right? You have Eulerian degrees of freedom typically for the fluid flow, but you could also have concentration fields in theory. So those would be Eulerian reference frame degrees of freedom. And then you have your Lagrangian degrees of freedom that kind of track, the configuration of the object. And this could be anything again. It could be particles. You could even use finite element solver. Whatever your favorite Lagrangian description for the material is, can be used there. And then these are glued together through these fluid structure coupling classes. And again, those can take any pair of Eulerian Lagrangian inputs, and they basically tell those two how to talk to each other. And then all of that's kind of enveloped in a stochastic integrator class that then is configured in a way that it can take pretty much an arbitrary Eulerian Lagrangian class that has a standardized interface and then integrates that forward. And so you really can pretty much benefit from the kind of combinations or combinatorial. You don't have to deal with the combinatorial complexity directly, since the universal interfaces kind of handle a lot of the high level things that you need to do in the various integrations. But from a modeling level, it gives you a lot of flexibility over things. And we've also allowed for custom force interactions, various types of XML interfaces and data output, so on. So if your integrator has some special feature to it, you don't have to rely on LAMMPS alone to output that data. But for all the kind of standard stuff related to molecular degrees of freedom, velocities, forces, and so on, LAMMPS will handle that for you. And there's many formats that it can output it in, including VDK formats, various MD formats like DCD files for BMD, XML, and so on down the line. Okay, and then at the high level, I guess I'll just point to this. The way this is all controlled is you got the Selm package. It kind of sits, next to the LAMMPS package, and the LAMP kind of has a hooks into the Selm package when it needs to do time integration. But from the outside, the way the Selm package is going to be controlled is through XML input files that kind of mirror each one of these coupling, Lagrangian, and Eulerian mechanics classes. So you can kind of configure each of those, live. Typically, you'll just have a Python script output the appropriate XML file. So that way everything can be just set in the Python script. Then there's a LAMMPS script, which traditionally was the driver for everything, but really now Python kind of takes the place of this LAMMPS script and kind of drives LAMMPS forward. And so that's going to be kind of the paradigm that we work in, that the Python script kind of tells LAMMPS, hey, go look for these files, load them in, set up your state in a certain way, and then tells LAMMPS, hey, go run for 1,000 steps or so. LAMMPS returns their state information that gets passed back to Python, like the particle configuration. So you can take a look at the snapshot of the current simulation, other state information, related statistics that we were computing, and so on. All that now feeds back into your Python script or Jupyter Notebook. So, so this has really been a nice new kind of innovation that you don't have to weed through endless C, C++ codes or some weird kind of custom scripting language that's distinct to the package. You can really do things now using kind of standard programming approaches in Python. So, okay, so that's kind of a very high level view. Like I said, I'll just give kind of like an overview in the beginning, and then I'll dive into the more interactive part in kind of the second half, or see how long it takes. But yeah, second half, or maybe the second 3/4, we'll see. Okay, so as I mentioned before already, we've been very motivated by problems in soft materials. So I won't say really too much about this. I did give a talk on this recently, and you can kind of look online for some of those. But really what we're trying to do here is target this kind of intermediate regime where you're not necessarily doing fully atomistic molecular dynamics. You know, that's very expensive, of course. And for many of these kind of material problems, you know, thinking about either passive or active soft materials, which are quite relevant to problems in biophysics as well as material science, it's prohibitively expensive to do kind of all atom simulations. And much of the phenomenology doesn't emerge at the fully atomic level. It's kind of related to how these mesoscale structures interact. So if you had something like a colloidal fluid, it's really going to be at the level of how these colloids are interacting. Now, there may be some electrostatics or even electrokinetics involved there. But again, you probably don't need to resolve this at the single ion level. You probably could get away with using Poisson-Boltzmann or some related simplified theory for the colloid-colloid interactions and get decent results. Same thing with a lot of these kind of biophysically motivated problems, you know, thinking about cytoskeleton and so on. Again, you probably don't need to resolve things down to the atomic level, but you need some kind of coarse-grained model for what the actin filaments are doing, you know, what the fluid is doing in between the active elements, maybe a little bit on the electrostatic side and so on. So we're really targeting this kind of intermediate regime. And what we're trying to do is get into a scenario where we don't have to resolve all the solvent degrees of freedom. So if you look at this solvated lipid bilayer membrane, very expensive. You know, the membrane in some sense only two-dimensional, but you spend all that calculation filling up the 3D volume because of the solvent degrees of freedom that are driving the self-assembly of the membrane. But there's been a recent push towards using implicit solvent models where you kind of build into the free energies of interaction, you know, the effects of the solvent degrees of freedom. And you know, you can quite effectively get fairly large length scales now where you have a sort of coarse-grained model of the membrane mechanics, which is useful for looking at, you know, how maybe a membrane might fold around a virus capsid or other types of interesting emergent mechanics, but without having to deal with all of the differential geometry and complexity that comes up if you try to take kind of a top-down continuum approach. So this is the regime we're really trying to target, is this kind of intermediate coarse-grained where you've thrown away a lot of the atomic degrees of freedom, but you've kind of kept the essential ones for that mechanism that you're trying to explore. And this does create a challenge because many of the mechanisms that are relevant to understand these material problems do involve fluid mechanics. You know, you've thrown away the solvent from the free energy of the potential interactions, but they still play a role sort of in the thermostat and in the kinetics, thermostating, I should say, in the kinetics of the problem. And that's what we really want to capture through some kind of continuum theory, so we can really get rid of all of these minute microscopic, you know, degrees of freedom that really probably aren't contributing all that interestingly to the dynamics individually. It's more the collective dynamics, which is really important. Again, it's a matter of, you know, particular problem that you're working on, how relevant those degrees of freedom are. And so I'm, again, targeting the case when you can kind of wash those away, but you still need it for correct correlations. Okay, so fluctuating hydrodynamics is a really nice way to go. I'm not going to say too much on this slide, just to mention that there's work that goes back to Landau and Lifshitz, where they introduced fluctuating hydrodynamic equations, and we're using approaches that are very similar. So this basically is the Navier-Stokes equations that you might already be quite familiar with. The main difference is there's a random stress there. And that's essentially what we're going to have also in our fluctuating hydrodynamic approaches. It's just that we want to couple this to microstructures of one form or another. So we can get the collective Brownian dynamics appropriate with hydrodynamic correlations, or spatially extended structures that have appropriate kind of hydrodynamically correlated Brownian dynamics. And so this is just showing here a little movie of these fluctuating fields that we're kind of replacing those molecular degrees of freedom with on the left. So in some sense, all of these small blue particles are being replaced on the right by this fluctuating hydrodynamic field that again, at some level is capturing the same kind of momentum transfer that's happening in that underlying material. So if you were to put a particle in here, and this is what we're going to talk about in a second, then you can basically simulate what I have on the left, but now with far fewer degrees of freedom. Okay, so the basic approach we're going to take is referred to as stochastic Eulerian Lagrangian methods. This is really, like I said, in the spirit of things like immersed boundary approaches. And the idea is you have two sort of overarching degrees of freedom. You have Lagrangian degrees of freedom that basically can live anywhere in space, and the Eulerian degrees of freedom, which typically will be discretized and fixed in the lab frame. And so you can have, point particles, you could have filaments, you could even have fully, volume encompassing elastic bodies. It really doesn't matter which case you're in. It'll all boil down to an appropriate choice for these coupling operators, one that tells you the kinematic response of the Lagrangian degrees of freedom to the material state, and another which tells you for a force or a stress that's applied, the appropriate way that that enacts on the momentum field of the Eulerian degrees of freedom. So the way I like to think of this is I like to start off with two momentum equations, one for the Eulerian material and one for the Lagrangian material, and then couple them together. And then one can go through various types of asymptotic analyses in order to tease out a model where, for example, the Eulerian degrees of freedom are enslaved to the Lagrangian rather are enslaved to the Eulerian degrees of freedom, like you would have in something like the immersed boundary method. But this provides a little flexibility in that you can, depending again on the phenomenology you're trying to capture, you can take a few different numerical tacks on the problem. And again, this is trying to avoid, in some sense, the body fitted mesh problem that you would have if you had two separate materials. You'd have to kind of keep remeshing in order to kind of get the appropriate traction stresses and things at the surface. That's all going to be folded into these operators, lambda and gamma, that I'm showing there. So the basic idea is you have the fluid equations, kind of like I showed on the previous slide, just abstracting slightly, because you can also do this for non-Newtonian fluids. This is a fancy L, which is the dissipative operator. Upsilon here is just a coupling operator between the Eulerian velocity. So I basically do a little averaging locally. I somehow process the Eulerian velocity field to get what it should be at a given point. And I look at what the Lagrangian velocity is. And I basically have a drag force here. So if velocity of the Lagrangian point is faster than the Eulerian one, it's going to kind of drag material along with it, and vice versa. And then this lambda operator converts kind of those point forces, if you want to think about this case on the lower right, as just to make this a little more concrete. This is basically taking point forces and turning those into force densities, which is what you need for the Eulerian description, which is all given in terms of momentum density, right? Okay, so this is basically just saying the equal and opposite force of a drag on your particle is essentially a source or a sink in your momentum equation for that surrounding fluid. And then the lambda here is the Lagrange multiplier. For example, you could have incompressibility constraints. And then the F therm is really the interesting part. That's how you thermostat the system. And similarly, microstructures, I have momentum equations for these, very close to the Langevin equation. The gradient x phi here is just the potential of a gradient, a force, conservative force that comes from the gradient potential. This is the drag force I was alluding to before. It uses, again, this reference from the Eulerian material to decide what the drag should be. You know, if you're going faster than the material in some sense, then there's a drag pulling you back. And if you're going slower, then you're going to get pulled forward by the fluid flow. So this is, again, very similar to what you have in Langevin dynamics, but instead of having it with respect to this kind of ambient ether, zero reference background field, now it's with respect to the fluid equations, which we're explicitly tracking. And then again, all that needs to be thermostated. And you have to do this in a self-consistent way. And it's sort of an interesting challenge because of the way that you're approximately accounting for these Eulerian and Lagrangian operators in the coupling. And so it turns out if you have an adjoint condition, all this can be worked out very nicely, and you can use fluctuation dissipation type principles to arrive at the thermal fluctuations that I'm showing down here at the bottom. Of course, it's a numerical challenge of how you compute these fields with the appropriate correlations in practice. But essentially what these fields are going to do is they're going to transfer spontaneously momentum from the fluid degrees of freedom to the microscopic degrees of freedom to balance that kind of drag term, which is of dissipative in nature. And so it's not going to actually lose momentum in the system, which is a little different than or a Langevin simulation. It'll just be transferring momentum from fluid degrees of freedom to microstructure or vice versa. And that's why it's so important that you capture this correlation that I'm showing at the very bottom. Okay, so that's the basic setup for pretty much all of the different numerical methods, whether you're talking about ones in the inertial regime, stochastic immersed boundary method, things like Stokesian, Brownian dynamics, and so on. You can look at them as various limits of this kind of overall setup when you take things like epsilon going to infinity to make the coupling tight, or the mass to be small, or the viscosity of the fluid large, and so on. Okay, so again, I just kind of put this in perspective. There's a lot of thermostats that are used in molecular dynamics which really aren't of a dynamic nature. They're really there just to kind of sample, in some sense, the equilibrium ensemble. Obviously here we want to capture some of the appropriate dynamics. We want to get correct autocorrelation functions, not just Gibbs-Boltzmann statistics. So Noisy-Hoover is nice for just getting Gibbs-Boltzmann statistics, but it's not really going to be something that's going to give you sensible dynamics in your MD, right? So of course, people resort to things like Langevin thermostats, and that's nice. And in some sense, our method is a kind of Langevin thermostat, just with a lot of degrees of freedom. And what you have here then is you have the particle momentum, but the typical way Langevin thermostats are implemented is like I'm showing here. You have your particle degrees of freedom. You have a sort of drag term, which is kind of like a sink on the momentum, right? And that's supposed to be modeling the solvent degrees of freedom, which you're not modeling explicitly here. That's the conservative force. And then you kind of, to get things to be the appropriate temperature, you thermostat by introducing a stochastic force that is this proportion into increments of Brownian motion. And so what's happening here is the particles kind of bleeding, its energy and momentum to this kind of ambient fluid, but the fluid really isn't moving or doesn't really have any state in and of itself. And then that's sort of getting pushed back into the particle degrees of freedom. And again, that'll give you the Gibbs-Boltzmann statistics, but often for many autocorrelation functions of interest, like if I had a material and I shear it, the fact that I'm not momentum conserving means that I'm basically going to lose a lot of the momentum in kind of an artificial way, and that kind of reduces lateral spatial correlations. And so I'm missing basically important degrees of freedom and mechanisms in the system. So the idea is that you can reintroduce those by these fluctuating hydrodynamic equations, where now all of that momentum that's basically lost from the particle is going to be explicitly tracked and kind of absorbed by the fluid degrees of freedom. And then through that thermostating I showed you on the previous slide, we're going to reintroduce that momentum back into the particle degrees of freedom in the appropriate way, consistent with statistical mechanics. And in this way, the momentum is actually not lost, right? If you sum up the total momentum of the system, you'll find that it's constant, even with the thermal fluctuations. And so this then results in a lot of lateral correlations then being restored to the system. That would be there if you had explicitly modeled all of those solvent degrees of freedom like I was showing you in the MD setting. So that's really the context of these techniques and why we're going through this kind of approach. Yeah. Okay, so that's the motivation. I'll just say one other thing about coupling operators. If you're not familiar with immersed boundary methods, one way you could couple your Lagrangian degrees of freedom is basically to have a little kernel function that basically does velocity averaging according to this kernel and moves the particles at that sort of local velocity of the underlying material. And then to get any forces if there are any forces acting on the structure, the way you can account for those in the momentum equations of the Eulerian material is then to spread those out using the same kernel function. And so one very popular kernel function that has certain nice translation invariance properties and so on is the Peskin delta function, and I'm just showing a picture of it here on the right. And you can use that with very effectively with point particle models. And for Brownian motion, I won't go into too much detail there. There's some interesting connections between how big you make this kernel and the effective diffusivity of your particles. So you wouldn't typically take that to be something that goes to 0. You would take it to be a finite size to kind of model an appropriate target diffusivity. You get Rotny-Pagner-Yamakawa type Green's functions or tensors between the particles at steady state. You can do other stuff like Faxon relations to have particles that tumble and translate as well, and so on. You can be very creative with these coupling operators, and that's where there's a lot of I think interesting directions to extend the techniques that I'll show you. Okay, so there's sort of these 4 regimes that we think a lot about in our work. The inertial regime is the one I showed you originally, but you can do various types of singular perturbation analysis, draw on tools from stochastic analysis to then get effective stochastic PDEs in these different contexts. This one is where you have very small mass, so I'm basically getting rid of the inertia of the microstructure, but still keeping some of the slip. This one is the regime that corresponds to the immersed boundary method, where I basically got rid of the slip as well as the inertia of the microstructure, so that everything is accounted for in terms of the underlying Eulerian material. There's an interesting issue that comes up. Again, I don't have time to really go into a lot of the details, but because this is a non-Hamiltonian formulation of mechanics, in other words, your momentum and configuration degrees of freedom are not conjugate to each other, you end up with this phase space compressibility. So you kind of have to generalize the usual Louisville theorem in statistical mechanics, and that's where this is manifesting in the stochastic dynamics. And then if you go to the overdamped regime where you set the fluid viscosity very large, you can do these effective calculations where you have quasi-steady flows. And that's this kind of last regime. And again, there's kind of these interesting terms that arise from the statistical mechanics and that non-conjugate aspect of the momentum and configuration degrees of freedom. Anyway, you can look at our 2015 paper for more details on that. So the techniques that we've developed basically fall into these different regimes. Some of them are quasi-steady state, some of them are fully inertial, some of them are kind of this immersed boundary style where you basically have the microstructure moving in sync with the underlying Eulerian material. Okay, so that's the overview that I wanted to give on the Selm methods. I'll just say a few words about implementation. I said in the beginning, I really don't want to dwell too much on this. Just that there's a very modular design, and I would welcome people obviously to extend with new integrators or new coupling operators, and very happy to talk further with people about how to do that in an effective way. We have a lot of templates to do that. This is just the graphical interface I was mentioning before that we developed. This is just something that would allow you to kind of interactively build up models and interactions. It's useful for certain types of fine tuning and things that you might want to do to your geometry. We were using it to make various types of polymer knots and other fun things with some students. But anyway, if people are interested in that and helping us upgrade that or have use scenarios, I'd be very happy to talk further about that. Editing points and stuff where you can move them around. Okay, so let me move forward to kind of the latest iteration, which is really the maybe preferred way to set up a model, and I think probably the most efficient one, which is to use Python and Jupyter Notebooks. And I'll have some precompiled binaries for 1804 and 2004 for Ubuntu. But okay, just to get the lay of the land, and then we'll kind of dive into an actual hands-on demonstration with the everything is in this package called User-Selm. This allows me to basically take all of our codes and pop it right into whatever the latest version of LAMMPS is. And then by issuing one command, if you're familiar with LAMMPS, you would do something like make yes user-selm. It'll copy all our codes in the appropriate place, and then you just compile, and now LAMMPS has all the Selm capabilities enabled. I put the examples as a branch off of there, just kind of in the spirit of that approach to using LAMMPS. And then, the way you would install it is you would compile it to basically a Python library. It's pretty straightforward. I'll have precompiled binaries if anybody's interested in. I'll put it in the package so that it's easy for people to get that set up for these distributions of Ubuntu. But basically, what you would do is you compile the shared library version of LAMMPS with our Selm, of course, incorporated, and then you just move it where you like or symbolically link it. And then there's a way to copy it into the site packages directory of whatever your favorite, environment manager is for, for Python. So if you're using Anaconda, you just figure out which Python, figure out where the Python is for that particular environment. Just go to the site packages directory, and then basically there's just 3 files you copy over there, and then now you have the Python interface to the Selm LAMMPS stuff. So I'll put a README in the package, and you can look there for more details. And in the Jupyter Notebooks, I put together some prototypes, and I'll go through this in a lot more detail when we do kind of hands-on, which is basically what you do is in Python, you just import the Selm LAMMPS package, and then there's this object, and you just feed that object commands to change the internal state. And that's how you set up your models. That's how you perform simulations, and then you can read out the state, and that's pretty much pretty nice. It allows you to set up all the particle locations, their interactions, ensemble that you're going to simulate, simulation parameters, and then how long you want to run it. Just because I can kind of show you a few different ways of running the codes that way. Yeah. Okay, and then we would go into simulation using Jupyter, IPYMD, right? So if we do that, that'll pull up the Jupyter Notebook. So is everybody gotten to that stage? I know it's a tall order, especially to maybe learn 3 or 4 of those things all at once or get them working on your laptop. But these are good items anyway to know, since they're kind of bread and butter things that you often need to do when you're doing scientific computing. So if you're not familiar with that, just read up a little bit on SSH, read up a little bit on Jupyter Notebooks, how to use them on a remote server, the tunnel, and those will pay dividends down the line as you do various forms of computational simulation. So is everybody with me? If not, just let me know, and I'll see if I can make some additional comments to help. But is everybody on this screen where I am? Okay, don't be shy. Just feel free to chime in if, yeah, okay, good. All right, I see some thumbs up. See, I don't know how to do that in Zoom, but that's good. Okay, so now the idea is, I've already compiled everything for you, so everything should work, because I got everything configured on this computer. It wasn't too bad. Play around a little bit with VDK packages and stuff like that, but everything compiles pretty readily. So basically what we're going to do is we're going to run through this notebook. And so this will really give you a very clear idea of how to set up a LAMMPS simulation. So this will be kind of like the first hello world kind of example for doing one of these stochastic immersed boundary style simulations. So in the beginning, I kind of have, a way that I set up all my simulations. So a lot of this could be stripped out, but I like to, tell the script what its name is so that I can use that for output directories and things. So you'll kind of get a sense of how I organize things. But at any rate, these are really the key commands, right? Here, this is the one that's obviously importing the LAMMPS package. Now you'll notice this one is IPY-LAMMPS. So that's for the IPython, the interactive Python kernel, which is slightly different than the standard Python kernel. And so they've implemented kind of 2 versions. But the nice thing is it all uses the same underlying shared library. So once you get the C++ codes and all that compiled, or you just download my binary, you're good to go. You just have to remember to change this. If you go to a Python script, you just remove the capital I. Okay, and then I like to use these standard packages here, just to kind of deal with logging and things like that. All right, so I'm going to skip these. These are just a bunch of utility functions that I included for logging and saving files and stuff. This is really back to the substance of setting up the simulation. So I'm setting up an output directory here. I have a little utility function I wrote to create the directory that we're going to output things in. I usually give the particular experiment a name, and then I use like, test 0, test 1, test 2, so on to get different instances of that outcome. I like to remove the directory before I start every time. That way, if I make a mistake and I have to rerun a test, I can just wipe everything and overwrite in the same location I was before. Okay, so that's just a little thing. You might want to comment that out though, because you have to be kind of disciplined about changing this, or you might overwrite a really nice simulation you got, and that has happened to me before. So, okay, you learn the hard way a few times, and then you're like, okay, I'm either going to comment this out, or I'm going to, after the simulation started, I'm going to change this immediately and save it so I don't overwrite those nice results I just got. Okay, this is just setting up again where I'm going to store the figure data, VDK data, so on. All right, so nothing really all that exciting there. This is creating the LAMMPS instance. So this is where we're going to get the object that we're going to basically interface with LAMMPS and Selm through. This is the L here. So I just store it in capital L, just kind of keeps the notation nice and succinct, although be careful if you use simulation parameters, capital L. You could name that something more complicated, but just kind of makes things parsimonious to keep it as capital L. All right, and then I wrote my own little utility routine to extract from capital L the version number and stuff so I can display that, because I like to write that to a log file so I know what I'm working with later on if I trace back results. Okay, and then this is where we're starting to set up the simulation, where what I'm doing here is I've created these kind of template XML files in this directory called Feeney-Dimer Model 1. And one of the nice things about, I'll show you what's in that directory now. We're basically going to copy all of those XML files. We're going to copy those into the the simulation directory that we're targeting. So if you look down here, this is showing where everything is going to output. Hold on a second here. Yeah, so continuing forward, this is all going to all of our output's going to go into this directory called simulation using Jupyter Fini test 0000. And so this just basically copies everything that's in this Fini Dimer 1 Model 1 directory to there. And that's useful just to have, you know, visualization scripts, whatever goes with kind of the Fini Dimer model stuff. You can kind of get it all there with the output so that it's all kind of nice and organized. So that's what I do. And I'll go into that directory in a little bit. But let me just continue forward. That's going to be where all those XML files that I was referring to that control the Selm codes, that's where they live. OK, then what I like to do also is copy the notebook itself to the output directory again, so that as I go forward and I develop new stuff, I can trace back easily. So that's what this does. And then this is where we're really getting into now the interface with the Selm LAMMPS library. So I like to use the docstring, the triple quotes, because then I can just write everything like it's in a text file, and it'll save all the line breaks and formatting. It's kind of like a raw string in some sense. And so this is what traditionally would have been done in a script file for LAMMPS. The nice thing about doing it this way is I can easily tokenize this, put whatever I want in here. For now, I just set it by hand because most of these are not so interesting. And so the main things really to point out here is the units that I'm going to use, that's given there, the angles, the atom style. This is all kind of LAMMPS terminology, and you can read the LAMMPS tutorial for more detail. But this is basically saying the atoms will not only have pairwise interactions, but they can also have interactions in triples. And so there's some data structures that, you know, are expensive potentially to compute. And so LAMMPS is trying to optimize and only compute the data structures it needs. So you kind of have to just give it a heads up that, hey, I'm going to have bond angles in this particular example, for example. Yeah. This is the bond style. Hybrid means I can have a bunch of different bond styles. Again, you kind of tell it up front what bond styles you're going to use. In this case, I'm just going to use Fini. The angle style, it turns out in this one, even though I made the atom style angle, I'll actually not use bond angle, so I just made that none. And then these are the boundary conditions. This periodic. I kind of put my own comments there because I find a lot of the LAMMPS commands a little bit cryptic, which is fine. They were sort of designed to be succinct. But anyway, so I've placed some comments there to kind of remind what they are. This is really an important line here. This is going to read in all of the configuration information. And so it's a little funny. We're doing everything in Python, but there will be a configuration file that I'll have the Python script kind of write out as kind of a meta piece of data that LAMMPS will read in. So there's a little bit of, you know, things that might be ideal to do through like a function call that I found just is more convenient still to just by writing basically a little temporary configuration file just provides a little bit smoother way of getting LAMMPS to operate and move forward. But there are ways you could do a lot of the things I'm going to show you kind of directly by calling that L class. I'm kind of building on top a little bit of legacy scripts and stuff that I've developed in the past. So this thing is nothing more, though, than just saying, what is the molecular geometry? And I'm going to go into detail of what this read data file is in a minute. It's like, where are all the points living initially? What are their bond types? What are their interactions? You know, how are they structured? Is what that's all about. So this is a very important line, even though it's just one line in this script. That's basically going to be where the entire model is specified. And then the rest of this is just things to do to the model, like how to initialize the velocities, how to, you know, set various cutoffs for the different interactions and things of that nature. But most of it, what you could do in your simulation is ignore most of these things that I've put in here and just primarily focus on the part of the script that writes this so-called read data file. Because once you have that, the rest of it will probably run pretty smoothly. Okay, this is another crucial line. This is basically telling LAMMPS to use our Selm integrator. They have these things called fixes. I think because originally their idea was to extend the molecular dynamics package where you could have fixed bonds and things of that nature. And then it kind of, you know, abstracted from there to being general types of interactions with the molecular model. So this is going to be our integrator right here, the fix Selm. This is basically just gives the name of an XML file that tells the SELM package, hey, where to go look for all of the parameter files for all of those object classes that are going to be involved. And then this last part is just for how I'm going to dump the data out. You know, what I'm going to do, I'm going to create some VDK files, some DCD files, things that I can use to visualize. And then this last step here is telling LAMMPS, okay, now that I've got everything set up, and I'm going to tell you a little more about some of those details, run it. You know, run this thing for, in this case, 100 steps. And then the last part is to write a restart file so that I could restart at step 100 if I wanted to later by loading that in. And that's pretty much it. So what I've done here is just created a little feeder. You know, like I said, you could have done a lot of things interacting directly with that L class. I like to just write one big string and then just feed that string in to the LAMMPS package. And so L command, I just feed it line by line by line, and it sets up the entire state of the LAMMPS package. Okay, so that's again kind of a quick sketch of the LAMMPS setup. I also just dumped the data out here so you can see it all. Also, that ends up in my log file nicely. Then you can go back and you can actually get state information. Like for example, you can retrieve from the last simulation. Let's just see where I do that. Here we go. You can get the atomic positions by just calling L atoms. That gets you this atoms object. You can get the number of atoms, and I can turn it into a nice little NumPy array. And now I can do whatever post-processing, whatever I want on the degrees of freedom. And so here I just made a little plot of the final configuration, and that's what you're seeing for the diagram. Okay, so that was a mouthful to kind of say all of that. The one thing that is really important for me to go into more detail is that read data file and show you how I generated that in this notebook. Because that's where all the geometry is, that's where all the interesting interactions are between the particles that make up the system. Okay, so let me go to that part of the notebook. I glossed over it just in the interest of not getting bogged down. Let's see where I put that. Oh, okay, it looks like in this example, I didn't generate the read data file. I just used one that already exists. But the next script does generate the read data file, because this was so easy. It was just 2 particles. Let me open that just so you can see what it looks like, though. Let's go in here. If you go, so traditionally what you would have done in LAMMPS is you create these read data files. Again, the way I would recommend to do this, and you'll see this in my Polymer example, is just have your Python code generate this. But this is what LAMMPS needs to set up the model. So I put a lot of comments in here because, again, I find these a little hard to remember off the top of my head. So basically, you're going to specify things like how many atoms are involved, how many bonds, how many angles. This is saying you got, 1 atom type, 1 bond type. This is talking about this box size. So the X low and high tell you like the lower left corner, the upper right corner. And then you can shear the box. There's this triclinic coordinates. We'll see a little bit of that when I do the shear example. That's all specified here. This is just the domain size. And then really my comments kind of tell the whole story. Now you're going to set up each atom type. You're going to say what the mass of each particle type is, or each atom type is. I'm calling them atoms, but they're really just coarse-grained particles. And so what you do then is you say what the XYZ coordinates of the atom are, and you give a little data along with the atom. So the atom has an ID that goes from 1 to n. It has a molecular ID, so that later on, if you want to visualize it, you can say, oh, which molecule, which structure did that atom belong to? For now, they're just all set to be 1. And then what type is it? The type, of course, is going to refer back to the mass, charge, other attributes you'd want to give to those atoms. Again, you can have XML-related parameters as well. So SELM can put additional information on the atoms. Like you can say, all right, all the atoms with these indices are of this structure or have this particular interaction for the SELM code. You can do that perfectly fine. This is just the LAMMPS side of things and how it's going to bookkeep. Then you have XYZ here, which is just the location. So that's how the atoms are going to be specified. And you'll see that down below here, because you have the mass, you see right there. You have the atom, this is of type 1, of molecule, sorry, this is index 1, molecule 1, type 1, and then it's at location 0, 0, -50. And atom 2, it's of molecule 1, type 1, it's at location 0, 0, +50. Then the bonds, I set up Feedy bonds, and so I just have to give the coefficients of that. So you have to read the LAMMPS doc for this, but This is just telling me what the prefactor is on the Feeney potential. This is telling me what the R naught is in the Feeney potential. So if I go to, let's see if I can do it real quick here. If I go to LAMMPS Feeney bond, you can easily see what where the bond coefficients will come in, and I'm showing you that here. So there's the actual potential that it's going to be computing, right? So that first one, it even tells you the order of them. K is the prefactor, R naught is this distance that's used in a Feeney bond. So what's great is I don't have to implement this Feeney bond. I can even have this Feeney bond interact with a Lennard-Jones potential by setting these other two numbers, epsilon and sigma. So there's all these things that have been kind of thought through that if you do these simulations from the ground up, often run into a wall that, oh my gosh, the Feeney bond is very stiff and it's running into Lennard-Jones bonds and so on. And should two that are in the same Feeney bond, should they be interacting with each other, or should I always skip the bonds? There's all these like special cases that become quite labor intensive to implement in practice. So it's great to be able to just leverage LAMMPS for that purpose. So that's what's being done right here in this line is we're using the Feeney. And then I can set up now the topology as I set up here with the bonds. You can see it's the bond ID, bond type, atom 1, atom 2. So this is saying this the first bond, it's of type 1, which means it's of this Feeney type. It goes between atom 1 and atom 2, and that's it. So, in a couple lines, you can see I can specify, the geometry and all of the interactions of my particles, at least within this bonded class. You can do non-bonded interactions as well, Lennard-Jones, other things like that. So really, really nice, and you don't have to implement any of that stuff from scratch. It's already been done in LAMMPS. You can really leverage that to get all of the potential forces that you need in the Selm method. Okay, so that's basically what's going on when I specify the model in this command, which is called, I'm just looking for it here, the read data command, which was pretty close to the top. There it is right here. So this is reading in that file I just showed you a second ago, and it's setting up all the geometry for this model. Pretty simple geometry here. It's just two beads connected. Okay. So moving forward from there, now we can actually run this script. And so the way to run it is just to click there. And if we do that, then this thing will go. And the real way to monitor this is to look at the upper right. There's a little icon, of course, that kind of tells us what's going on. So if we look in the upper right here, we see this thing flashing. If you don't see that flashing, I will say, if that stops flashing, then there's an issue. Okay, so here you can see it just got down to this line. I'm printing out the last atom position, and there's the plot of the last configuration of the simulation. So it all ran for those 100 steps, and that was the outcome we got. Okay, so that's the Feeney bond example. Any questions about that? And I'm going to go through a more complicated example in a minute that does more than just compute the interaction between two particles. So everybody with me? Everybody get that to run in their instance of the Selm LAMMPS? Yes? No? All right, I see a thumbs up. That's great. Okay, so next on the list is to then look at this polymer example. So this would be in the directory, just to kind of walk you through it. It should be in the directory given by, let's just go back here so you can see it. Go to examples, polymer 4, and then if I go to polymer 4 model, or just polymer 4 in general, then it's the simulation underscore polymer 4, okay? So click on that, and then that will lead to this file right here. And so now the idea here is we can do something very similar to what we had before. It's the same basic setup. What's going to be different about this one is the topology is a little more complicated because now we have an actual polymer. I'm going to make a polymer knot, in fact. I'm going to put it in the form of a figure-8 knot. So if we go through here, I'm going to set up harmonic springs. Really, the only thing that's different from what I showed you before is instead of having the read data be this thing I crafted by hand, the script is going to craft the read data file for you. And so this is just setting up the box size. This is setting up the atoms. This is now setting up the polymer points. And I used a bunch of little Python data structures just to kind of do the bookkeeping so that I keep everything straight between the atom types and their names and how I want everything to line up. But it's not really that complicated. Really, this is where the geometry is being generated, really these 3 lines. Everything else is just bookkeeping, so I can generate a nice atom list, bond list, angles list, etc. So the basic model setup is going to be a bunch of points that make up a figure-8 knot. They pairwise interact to give you harmonic springs. And then in triples, they'll give you a little bond angle term, so it doesn't want to bend. Okay, so this is setting up the geometry right here. I just made a little parameterized curve of points x, and then I assign them atom IDs. That's what's being done right here. And then what I do is I just save that in a little data structure called atom ID list for that particular atom type, and names and other information. Okay. Then I go down and I create a bunch of tracer atoms. So I'm just going to have a bunch of diffuse atoms in the 3D bulk surrounding the polymer. Set all those guys up and store those in an appropriate Python list. Same thing with the bonds now. The bonds, which I do is I go through and I basically just really the information that's interesting is down here. I just set up a bond so that the first atom binds to the second one, the third one, so on down the line. All the way around, coming back to where I started. Okay, and then what I do thirdly is I set up the bond angles. That just occurs, the most interesting part of the code really is here. That just occurs between the triples. So I'm just going to get triples going down the length of the polymer. Okay, so I do all of that to just set up these little lists in Python. And then what I do is I generate, I save those to a pickle file, but then I generate the read data file. So this is just taking the basic template I showed you before, and now I'm just going to start filling in things from the Python data. So this is just filling in the number of atoms, number of bonds, and everything from what I actually computed. So this is just going to generate for me a read data file that corresponds to all of those data parameters that I set up before. So this is just going to set up the atom masses, the atom locations, the bonds, their topology, the angles, the angle bonds, and their topology. And then if I look at what I've generated at the end here, you'll see that, let me just do this. Yeah, so if I do that, I guess I have to run this from the top or else it's not going to work. All right, this is where I need to be careful about not overwriting nice data that I had before. Let's see which computer I'm on here. Let's see, that should have gone. Let's see here. Okay, let me just run this from the top so that I can show you what that file looks like that it generated. Okay, there you go. So you see it right here. Okay, so obviously you don't want to write this by hand. You'd want to do some kind of scripting to get this. So this is now the outcome of all those commands I showed you. It generates the read data file on the fly that now gives you the entire configuration of the model. Now, the reason why there's so many atoms here is I have the tracer atoms plus the polymer atoms. That's what's going on here. See, coefficients, bonds, so on down the line. Okay, and all of that, if you were to plot it, looks like this. Okay, in this particular notebook, I made an initial plot. The initial configuration is plotted. So you see, it's this nice little figure-8 knot. We'll see a nicer plot in a minute in 3D, but this is just 2D projection of it. And then all these little blue points are going to be tracer points that I put in the simulation, so you can see everything. Okay, and then as I said before, you go through, issuing those Python commands, and really the main one here now is just, tell it to run for 1,000 steps, and that's what it's going to do. And then you can still, get the last configuration, all of that, and when it completes, it'll make a plot just to show kind of where things ended up. All right, so that's the basic procedure. So pretty straightforward to get simulations going with the Selm LAMMPS library. And again, the right thing to do is just to reach out to us if you're interested in using these things and simulating stuff, and we can kind of work with you to help adapt things to your particular problem. Okay, let me show you how to visualize this. So if you notice here, there's this rsync sim script file that I wrote. And this is a good thing. You can just, in the browser, click on it, just cut and paste it into a text file on your local machine. And then you just basically run this. And you'll have to update the output directory so it's the right one. Here I'm just using user template. So you update that to your username. And then if you run this in your in a local directory, this will copy all of the files to your local machine that was from that simulation that I just showed you a minute ago. So let me go through and show you what you would get out of that. Probably the easiest way to do it is here. I'll just go through the Python interface. So everything's going to be dumped down in this harmonic test 00 directory. These XML files and everything, pretty much most of the stuff in the base directory came from that, that model directory. So I kind of have these templated models. And as I said before, there are these XML files that drive Selm. So if I, again, you can look through the documentation for more detail on this, but this would be the XML file that's kind of the master one that tells the rest of the code what to do. And it pretty much tells it like what base names to use, random seeds, what Lagrangian degrees of freedom to use, what Eulerian degrees of freedom to use, what coupling operators to use, interaction operator to use, etc., integrator, and so on. So that's it, right? So you just, if you want to change, from using this LAMMPS shear integrator to something else that's available, you can just look through the source code and you'll see names of files. You can just change that here. Now, what happens is that this one is kind of telling LAMMPS at a high level what to do. In order to get the specific files worked out, let's say for the integrator, since that kind of drives everything, there's going to be an XML file that has the name of the integrator, .selm integrator. That's also an XML file. And then what you get here is you basically get the following, right? You have the viscosity of the fluid, the density of the fluid, the Boltzmann constant, the temperature, and then you see you have the shear data here, right? Which is telling it how to, what kinds of shear to use, this kind of Lee-Sedgwick boundary condition stuff. And that's it, right? And then whether I should turn on or off is just a flag for turning on and off thermal fluctuations, which can be useful for certain tests. And same thing with turning on off incompressibility. And so all of the Selm code that use, in this particular simulation, that use this integrator will refer here to get those key parameters. And so it's really easy. You just change this text file and now the codes will behave accordingly. And again, you can use Python to just tokenize this thing and have this output as part of your Python script. Or like I've done here, you can just have it in that template directory that gets copied to the output directory when it runs. And then there's similarly other ones for doing stuff like the Eulerian, Lagrangian, like the mesh, which is going to tell you, how many degrees of freedom in each direction you have in the mesh and where the center of the mesh is and so on down the line. Oh, and even in this case, there's some related to outputting various VDK data that's associated with the mesh. So that's how you kind of control things. And I put a few visualization scripts in here too to kind of help a little bit with seeing the model. All right, so that's the basic setup. And I mentioned the outputs then will get dumped here. This is a log file for the LAMMPS stuff. The main log is everything from that Jupyter notebook that I logged. Let's see what else would be of interest here. And then the actual configurations are going to be in this VDK directory here. Oops. So this is going to be a pretty big directory. So I think that's why it paused on me. Here you go. So these are all the snapshots of the bounding box and the configuration of the particles. Okay, now what we're going to do is what do you do with all this output, right? You got a bunch of data. You want to visualize it. So that's the next thing I want to discuss briefly. Okay, so the way you would visualize your data, and let's see if I can get it to work on this live demo. What you would do is you would go into the output directory, and that's what I'm doing locally on my machine, and I'll share my screen in just 1 second with all of that. And then I'll show you how to visualize the results. Directory. You see how I have these different scripts. Some of them will run through the VDM package, some of them will run through ParaView. And so if I do something like this viz pv polymer 4, you can see this will actually pull up the model. You'll get this, right? So this script will pull up this visualization of the model, right? So this is the model polymer 4 that we just ran a minute ago. And so you can see it has a nice configuration of a figure 8 knot, right? And then what we can do then is we can play a movie of that. And this one, I believe, is just passively thermally diffusing. And so let's do that with maybe 200 frames, probably a good time to do it. Yeah. And so you can see it now diffusing here In fact, I think it only has 1,000 frames, so maybe we'll do this one with 50 frames, maybe go 4 times faster. Okay, so there you can see the polymer passively diffusing. The blue points are all the tracers. You can kind of see that there's hydrodynamic correlations incorporated and so on. Okay, and that came from the simulation that you just ran a few minutes ago. Okay, any questions about that? Is it working for everybody on their end? Yeah, and so the basic idea for the Jupyter Notebooks is you have this creation of the LAMMPS-Selm instance. You issue commands to it, right? And you can look at the LAMMPS documents and my documentation for how to do that in detail, or just look at the Jupyter Notebooks. So the basic steps are that you set up this model geometry and interactions in Python. You export those to a generated file, like a read data file and whatever XML files you would need for the Selm codes. I have the template files there. And then you basically use Python then to set up that sort of prototype LAMMPS script, and then you run the simulations, and then you can do intermediate checks. So you could run the simulation for 10 time steps, then go make a plot, look at it, continue running, right? And you can even get state information and everything from the simulation platform. And in theory, you could also perform various forms of analysis on this intermediate data as well using that protocol. How to set up a practical example using this simulation Polymer 4, which I showed here on the right. And we kind of went through that together. And the basic idea, again, is you can use Python to set up this figure-8 knot, its bond interactions, its angle bonds, very easily using the LAMMPS. And then we can simulate, and the outcome we got for passively diffusing particles is shown here on the right. Okay, so we think that's probably a good place for me to wrap up, but I'll stick around if people have a few questions or things of that nature. So yeah, so these are these stochastic Morse boundary methods. These are the main papers, on techniques that I've talked about here. I guess you can also refer to this page if you want to get kind of a more comprehensive list of these recent stochastic Morse boundary techniques that we've been working on. Good talking, everybody, and thanks for joining me today.